What I'm going to talk about now is once you've done the experiment and you have your initial data set, what information does it give you? How do you analyze it? And how do you know if things are going right or wrong? It's a long talk, so bear with me. Please ask questions as we go along. And I'm going to start out by kind of going over once again what Xiaobing did in the first talk about what the scattering profile is, how we get it, because this is the fundamental unit of data. If you come away from a SAXS experiment with data, you're going to have a scattering profile or multiple scattering profiles. Then I'm going to talk about what can go wrong with your data, how all the things that Kushal was talking about might manifest in your experiment and what that'll look like. Then I'm going to go through 4 basic analysis techniques that you should do while you're at the Beamline to verify data quality. We'll talk both about what information that gives you about your sample, and we'll talk about how the different ways your data can be bad manifest there, so you have tools to kind of analyze and determine whether or not you're getting good data while you're at the Beamline, and ideally have the ability to make corrections on the fly if something's going wrong. The nice thing about SAXS, it's in solution. It's not like you have these crystals or frozen grids. So if you do an experiment, the solution isn't bad, the buffer conditions aren't right, something doesn't look good, we can make an adjustment and then do the experiments again if you have enough sample. So we have that capability, so it's very important to have real-time feedback while you're doing your experiments. All right, so we're starting again from the top. I'm going to talk about the scattering profile. What we have is we have X-rays, here represented as plane waves, coming in and scattering off of electrons in a molecule. We can schematically represent that scattering as circular waves. We measure it somewhere further away on the detector. I should also acknowledge I borrowed these images from Richard Gilliland's workshop at MacChess, which is where I first did SAXS. So it's more usual to not represent all these wavefronts individually, but instead we represent them sinusoidally. So that's what I've drawn here. And so this is the picture that Xiaobing got us to. I don't have the equations up here because you've seen them, you have them, and they're probably not much use to you unless you spend a week kind of playing with them. But the fundamental idea is when the X-rays come in, they're in phase. They scatter off of, in this case, we're considering 2 different electrons. And then at some angle far away, we measure the 2 waves coincident on the detector. Now, the issue is, or not really the issue, but the caveat here is that because there's an angle, one of these waves has to travel further than the other one to get to that point on the detector. And that means there's a phase shift. And as you know, if you've done kind of any introductory physics with waves, when you have a phase shift, the waves add, and they can either add constructively or they can add destructively. When they add constructively, you get bright spots. When they add destructively, you get low intensity spots. And so from a single particle, we end up getting this kind of speckled diffraction pattern. Now, of course, we can't actually measure a single particle. You can come slightly closer at X-Fells. You can get speckle patterns there for various ways. But what we measure in solution is we have a bunch of molecules, right? Large numbers. One of them's pointing that way, one of them's pointing that way, one of them's pointing that way. And it turns out that as they're in solution, they're tumbling, they're pointing in all directions. What you're really measuring is the equivalent of the particle oriented in all directions. It turns out that the measurement of a bunch of particles oriented in different directions is the same as the measurement of a single particle averaged over all possible orientations. And what that does is, as it blurs out the molecule, essentially, it blurs out that speckle pattern into this nice kind of sunrise. This kind of image is the kind of thing you'll be collecting at the Beamline. You get these 2-dimensional X-ray detector images, essentially the camera for the X-rays. But there isn't 2 dimensions of information in these images. Unfortunately, it'd be nice if there were. But it turns out that if you you start at the beam center, wherever the beam is hitting the detector, and you go out some radius from that, and then you go around in a circle at that radius, at constant radius, the intensity is always going to be the same within the noise of the measurements. Or at least it should be if you have a good system. Mechanical issues can throw that off. But the theory is it's the same at all radius. And this is, I think, relatively intuitive to understand, right? If you have a drop of sample and you make a measurement, and you turn that drop 90 degrees, and you make another measurement, you expect the detector image to be the same, right? Because the molecules in the sample are randomly oriented, they're pointing in all directions. There's no preference if it's like this or if it's like this. On the detector, then, if we turn this detector 90 degrees or any arbitrary rotation, we ought to have the same scattering at whatever point we were looking at. And that's a rotational symmetry argument. And it's basically just saying at any radius, constant scattering. So instead of working with these two-dimensional images, we average, we get better statistics. And what we end up doing is you go out to some radius, you average around in the angle, like I'm showing in this bottom right plot. You do that again at the next radius, and the next radius, and the next radius, and you create this one-dimensional curve, which is scattered intensity versus essentially distance on the detector. So this curve is your scattering profile, but I'll talk more about kind of how we usually represent it in a moment. But a few caveats. So I said you go some distance on the detector, you make the averaging. Mechanically, that's what happens. But distance on the detector is not a useful coordinate when you're talking about your data, because where scattering ends up on the detector depends on how far away the detector is from the sample, what wavelength you're working at. We really want some kind of geometry and wavelength independent way of talking about where the scattering is. And it turns out that what we use is the scattering vector, Q. So if you do out the math, if you go back to Xiaobing's equations, you'll see that Q is actually the difference in the incident and exit wave vectors. It's K minus K prime, or maybe K prime minus K, if I can remember my directions. It's represented, it's calculated as 4 pi sine theta over lambda, where theta is half of the scattering angle. And just kind of schematically in your head, you can think of it as representative of where on the detector you are in a way that's independent of where you put the detector in physical space. So if you plot your sample, your data as intensity versus Q, if you go and you measure it on a different beamline with a different detector at a different energy, you still ought to get the same intensity versus Q plot. So this is the kind of independent way to reduce your data and compare it to what's going on elsewhere. If you're a crystallographer, or you've done crystallography at all, they use an S vector. Q is 2 pi times S. So it's the same reciprocal space vector. The other thing I'll mention is that we are working in a scattering space. So Q has units of 1 over angstrom. That just comes out of the math. It's reciprocal space, it's inverse space. Whenever you're thinking about scattering profiles, you have to think about them in terms of 1 over distance space. And I'll give you some real examples of that in a moment. So this is an equation that's been up on the board a lot. This is intensity. I've written in terms of mass and concentration. There's a few things I want to emphasize here. So we've talked several times about molecular weight and concentration playing into the scattered intensity. What this means is that bigger things scatter more, given the same concentration. So if you want to get the same scattering from something that's small and something that's big, you need more concentration of the small thing. This is fundamentally how we determine how much concentration we need for an experiment. How much signal to noise do we want to get, and what's the concentration you need to get that. But additionally, there's other parts to this. There's the contrast term, which I'm going to mostly ignore, but basically it's telling you that you're measuring the protein and the buffer, and you're looking at the difference. There's a term that's giving us the shape, which we call the form factor. Again, for crystallographers out there, unfortunately, if you're a crystallographer, this is not the same form factor as in crystallography. For historical differences, the fields use different terms, and you just kind of have to deal with it, I'm afraid. So we're too far down that road now to change. So there's the form factor, which gives you molecular shape, and there's the structure factor, which gives you something about the intermolecular interactions. And so generally speaking, when we're making a SAXS measurement, what we're interested in measuring is the shape of the molecule. And so that means we generally want the structure factor to be 1. And I'll talk more about how you get that later, but it essentially means you need your solution to be dilute enough, and you need your buffer conditions to be correct, that the particles aren't interacting and having some kind of influence on each other. This is how the scattering profile looks mathematically. Important points: scaling with mass, scaling with concentration, has a structure factor term. On the plot 2 slides back, I showed you intensity on the x-axis and Q on the y-axis, so that corresponded with the detector image. But generally speaking, we think of intensity as a function of the scattering vector, I of Q. So when we plot these things, we plot I of Q on the y-axis, Q on the x-axis. This, again, actually should look familiar from Xiaobing's talk. This is one of the few things that we can analytically calculate the scattering profile for. This is a sphere. The equation is not terribly important. But what is interesting is I plotted for 2 very different sizes of spheres the scattering profiles. Now these are the same equation, this is the same profile. All I've done is I've changed the radius. And this illustrates, I think, kind of nicely what we mean when we're talking about Q as a reciprocal space vector, as a 1/distance vector. If you consider the features of this to be these dips, or the dip plus the peak, for the smaller thing, the features have moved out to higher Q, right? Smaller things are bigger in 1/size space. So the features of the smaller profile are scooting out towards larger Q. The features of the larger profile move in towards smaller Q, right? 1/something big is something small. This holds for all the kinds of size information. Xiaobing had this nice plot in his first talk where he showed you, in this regime down here, you get kind of information about overall shape. And then the next regime out, you get information about kind of conformation. And then if you continue going further out and you can make really good measurements, you start getting information about the internals of the macromolecule. And so whenever you're looking at scattering profiles and whenever you're thinking about scattering profiles, the thing to keep in mind is that all the stuff down at small q, that's all coming from the overall sizes, basically, and from the larger dimensions of your system. Whereas the stuff out here, the stuff at larger q, is coming from the more finer details and the smaller dimensions of your system. In theory, if you went out far enough, you could measure atomic level resolution. That's actually what crystallography is doing. It's basically taking this scattering pattern, overlaying it on Bragg peaks, and measuring it way the heck down at this end of the plot. It's a bit of a tricky thing to get your head around initially, but it is, I think, an important point. That's a little bit about scattering profiles and how we generate them, just kind of a review from the earlier talks. I also just wanted to review what a typical SAXS experiment looks like. We have an X-ray source, we shine it on our sample. This part is very complicated, but you don't have to worry about it. The sample part you do have to worry about. So it scatters off the sample, and we measure that on a detector. But as Kushal mentioned, and I think Xiaobing mentioned as well, the scattering from a macromolecule is not that much larger than the scattering from the buffer that it's in. So if you measure a protein solution, you then have to measure the buffer by itself, and you subtract the two to get the scattering from the protein by itself. I've shown this here. Schematically, I've actually shown this with real data on the bottom plots. And so what we're seeing here is a protein plus buffer scattering in purple, buffer in blue, and then protein in red. This is how we actually carry out an experiment. We get a single profile, perhaps, or we get a bunch of profiles, depending on what we're doing, for the macromolecule by itself. And so that, in theory, kind of takes us up to the end of Kushal's talk, where we have some data, and we want to now start thinking about how to analyze it. But before we get there, I wanted to talk about how we visually look at the scattering profile. Question? Yeah, so the question for the remote viewers is, if you want to compare 2 proteins under the same conditions, say mutant and a wild type, is it best to have them in the same buffer? The answer is yes, but that's mostly because of the biochemistry of the system, right? If you want to compare them directly and you want the same biochemistry, put them in the same buffer. But once you've done the buffer subtraction, there shouldn't be any contribution, the scattering from that component. So it's all a question of how the chemical composition of the buffer is affecting the samples. So if you want to directly compare them under the same conditions, yeah, put them in the same buffer. That's probably your best bet. Visually representing scattering profiles. You're going to see plots of scattering profiles all over the place in all of these talks. And I just wanted to give you a quick note on that. This is the same scattering profile on 3 different plots. On the left, I'm showing a linear y and a linear x-axis. Then I have a log y and a linear x-axis, and then I have a log y and a log x-axis. So lin-lin, log-lin, log-log plots. You essentially never want to use a lin-lin plot. I don't want to see this. And the reason is that your scattering profile, if you look at this log-lin plot, it's covering 3 or 4 orders of magnitude in your measurement. So when you put a linear y-scale here, you're hiding a huge amount of information and variation in the profile that you can't see, and it can be extremely deceptive. So unless you have a particular purpose for putting it on this plot, I recommend you don't. The log-lin emphasizes the mid to high Q region. So this is the plot you want to use if you're trying to emphasize, say, shape or fine structure differences. The log-log emphasizes the low Q region. So this is what you want to do if you want to look for size differences in your sample. So they have different purposes. There's also a bunch of different plots that we use for particular analysis. But just generally speaking, if you're presenting a scattering profile and you're showing it in a group meeting, in a paper, in a presentation, or wherever, unless you're doing a particular analysis or you have some particular reason, it ought to be on either a log-lin or a log-log plot. Now, what I want to do is I want to spend some time kind of going through some of the things Kushal talked about, talking about what can go wrong with your data, and then I'm going to show you how that looks in the scattering profiles. And then, once we've done that, we'll go through the basic analysis tools in our toolbox, talk about what they are, what information they give you, and how they can tell you whether or not your data is bad. Ideally, you'll get good data, but at some point you're not going to. And so being able to identify bad data is very important. What can go wrong with your data? Generally speaking, there are 4 main things that can go wrong with your data. There's a lot of other stuff, but it all boils down usually. Either you have bad quality sample, and this usually means aggregates, either generic aggregates, a different protein, or some kind of unexpected oligomers in your solution. That's going to mess up the measurements of the sample that you came here interested in. You might get radiation damage. So it turns out that biological systems aren't very happy getting X-rays shown on them, right? This is why you have to wear the lead apron when you go to the dentist, because the X-rays could harm your biological systems. The same, though on a much different scale, is true for proteins. And so the very probe that we're using to get the information can actually change the results of the experiments. And radiation damage will manifest as unexpected time-dependent changes in your measured scattering profile. There are cases where you go in looking for time-dependent changes, and that's a different story. We'll talk about that this afternoon. But if you're expecting a static system and you see time-dependent changes in the profile, that's almost certainly radiation damage. And that usually manifests as aggregation. So again, it circles back to this point. You get aggregates, and that's going to mess up what you can measure about the sample and solution. The third thing that can generally go wrong is you can have some kind of structure factor, right? It's that multiplicative S of Q term in the equation for I of Q. You get a non-unity structure factor, something that varies from 1 and varies with Q. And then you're no longer measuring just information about the shape of the macromolecule. Now you're measuring information about the shape of the macromolecule and its interaction with the other stuff in solution. Generally speaking, that's not what you come here to measure. There are a few people who are interested in these interactions. They do that, but most people are not. This usually boils down to concentration effects, and it will manifest as concentration-dependent changes in your measured scattering profile. Typically in the profile, what you'll see is either an uptick or downturn at low Q, and I'll show that in a couple slides. The final thing that can go wrong, and kind of the most insidious in some ways, is what Kushal mentioned. You can have bad buffer subtraction. If your buffer match is not good, when you do the subtraction, because the protein doesn't scatter that much more than your buffer itself, you carry out the subtraction, it's going to mess up the profile that you measured. Even a little bit off can throw off your results significantly. And typically, this will look like either the profile going negative at high Q or low Q, which is over subtraction, or the profile being offset at high Q and having an uptick at low Q, which is under subtraction. And it may be either or both in those cases, because depending on how you've messed up the buffer, it may be an overall shift, it may be a shift at low Q, it may be a shift at high Q, depending on what the differences are. You can also get bad buffer subtraction if you, say, have protein that gets damaged and then builds up on the capillary walls that reads like background in your scattering, you subtract it off, and it shouldn't be subtracted off. It shouldn't be there at all. So that can also show up as a bad buffer subtraction. So what do these look like in a profile? Well, aggregation is kind of the most common thing you'll see through various effects. And generally speaking, what that looks like is an uptick at low Q. So again, these are generating larger size things in solution, or you start with larger size things in solution. They're going to scatter at low Q, right? Because that's where big stuff comes in. You can see here we have a profile with the unaggregated system in blue, and then when you have aggregate in it, it goes up into this red one. There's this big uptick at low Q, and it looks actually pretty terrible. This is an extreme case. You can have smaller amounts of aggregation. I'll show something like that later. Radiation damage typically manifests as aggregation in your system.
Can I ask a question?
Yeah.
How do you identify?
Oh, that's a very good question. And in about 3 slides, we'll start talking about the Guinier fit, and that will have a significant analysis and validation for aggregation. So for the remote viewers, the question was, how do you tell from the curve if it's aggregated? The answer is usually do a Guinier analysis, and we'll get there. So thank you. Radiation damage. So typically, this manifests as aggregation, which means you're going to see the same increase at low Q. It's going to go up. Here I'm showing 3 profiles, the beginning, the middle, and the end of a sequence of exposures taken on a sample. And it's changing across those profiles. That's what we mean by a time-dependent change. You see a change in the profile as you collect your data. The damage is happening, and in this case, it's manifesting as aggregation, which shows up as this uptick at low Q. So interparticle interaction. This usually comes from concentration effects. So what I'm showing here are 3 different concentrations of the same protein. It happens to be lysozyme. So low concentration, you have the blue curve. Then as you add more and more concentration, the curve comes down. This is very characteristic of repulsive interactions. It lowers the low Q. This is, again, something that we'll be able to see with the Guinier analysis. A little bit more on interparticle interactions. As we said, it's this multiplication of the form factor, which is the shape information that we're interested in, with the structure factor, which is something we're typically not interested in, to produce a curve that isn't just the molecular shape anymore. So it's corrupting our data by adding in this information of the structure factor. So typically we try to adjust the concentration and adjust the buffer conditions to avoid getting these interparticle interactions. And looking for these is very important in your data set. So the final thing that we can see in our curves is subtraction errors. So here I've artificially created subtraction errors just by changing the offset of the buffer by 3% in either direction. Relatively small change. And you can see the blue curve is what it should look like. So when the buffer is 3% high, there's a downturn at low Q, and it's actually, the profile's gone completely negative at high Q. Whereas just a 3% low buffer ends up being this offset at high Q, and we have an uptick at low Q. So again, we're very sensitive to these buffer issues, and having a good match is very important to getting good scattering data. So that's what things can look like when it goes wrong. What we're going to talk about now is various analysis techniques that let you tell if it's going wrong, and can also get you some other information about your data set. I'm going to go through them essentially in the order that you would do them at the Beamline once you have a profile. So typically we get a profile, we get the buffer subtracted curve. First thing we're going to do is Guinier analysis.
1. What will be low buffer subtraction? Well, I have to revisit this.
So the question is, what will be low buffer subtraction? So I'm not sure if there's 2 ways to interpret that. So one is that low buffer looks like this black curve. It doesn't subtract off enough of the signal. What I think they might be getting at is, when does it happen? And the answer would be, for example, suppose you make up a matched buffer by hand. And the matched buffer you run for the subtraction doesn't quite have enough salt in it. It's going to have a little bit less scattering than what the buffer you measured your protein in. And so when you subtract it off, it's not going to subtract out all the scattering from the salts, and you end up with this offset on your scattering profile. Hopefully
Which is why we recommend that you never make buffer separately The way to match buffer is dialysis. They're doing a batch modeling.
Yeah.
It's not a factor in size exclusion chromatography SAXS. Another advantage. But yeah.
Question?
He just answered it.
Okay.
I was wondering if the problem really was relevant to SAXS, but I suppose.
Mostly not, though you can if you have mismatched buffer in SAXS. So the question is the problem relevant for SAXS? Generally speaking, no. But if you have a significant mismatch, you can get the small molecules eluting at the end of the sec elution. And if that happens to be where your protein also elutes, then you still don't get a good buffer match for SAXS. And so in that case, we do recommend matching as well as you can for the sec buffer. But the sec buffer is a case where, for example, if you mixed up a match by hand, then you ran it in sec, it's probably close enough you won't get that small molecule elution peak at the end, and it's not going to potentially mess up your data set. All right, so Guinier analysis. This is typically the first thing we do with a subtracted profile at the Beamline. And so I'm going to start by telling you what it is, and then I'll tell you why it's useful. So Guinier analysis was developed by André Guinier in 1939. This is my only historical note, and the reason I mention it is because André Guinier is generally considered to be the father of small angle X-rays. He's the first guy who kind of sat down, and it was his thesis advisor, actually, who told him, there's all this smudge around the beam stop. Why don't you figure out what that is and if it's useful for anything? Figured it would take him a year, something, right? Turned into a field that spanned, more than 80 years at this point, I think.
What was he trying to look at?
He was looking, I think, at samples of carbon black was the first scattering experiment, and they were just curious if all this scatter around the beam stop in their crystallography data had any meaning. Basically, start with the easiest diffraction spot, the 0, 0, 0 spot, and can't tell you anything. And then it went from there. Named after Guinier himself, this analysis, it's actually relatively straightforward in concept. So the idea is that for any scattering profile, if you look at low enough Q, if you let Q go towards 0, you can approximate the intensity of that scattering profile as I of Q equals the intensity at the 0 angle times an exponential decay in Q squared. Now, it turns out this is just purely a mathematical coincidence. It's an agreement in the first, I think, 3 terms of a Taylor expansion of the 2 forms, and it only holds for this low Q range, but it ends up being very useful. So this is true for a single monodisperse thing in solution. So if you have other stuff, you get multiple Guinier ranges, and it starts getting a little weird, and we'll show that in a moment. And there are 2 useful pieces of information that you get out of this. There's the scattering at 0 angle, this I of 0, more commonly what we call it. And that is proportional to the mass times the concentration. So you can use that to get information about the molecular weight of your system. And then in the exponent, there's this Rg. This is the radius of gyration. You'll hear this come up a lot in SAXS, partly because it's usually the first parameter you get about your system. And this has something to do with the size of your macromolecule. And on the next slide, I'll talk a little bit more about what it is. So essentially what you do if you want to see the Guinier range, the conventional way to do it is you plot the log of the intensity versus Q squared. And then the linear region of the profile is where the Guinier approximation is holding, right? If you take the log of this equation, you end up with some intercept plus or minus Q squared Rg squared over 3. So if you fit this linear region then, just nicely to a line, it's a very easy mathematical thing. The slope gives you the radius of gyration, and the intercept gives you something proportional to I of 0. So it's a very simple analysis. You just make this transformation on your data set, you fit the linear region, and off you go. Turns out it's not quite that simple, and in the next slide I'll get to that. But first, I want to talk about what the radius of gyration is. So in a formal definition, it's the RMS distance from the center of mass. There's some various ways to calculate it in various different formulas. I put those up there for your reference, not to go through them in this talk. This is the same picture Kushal showed, except he has a newer version that's much better quality that I may steal from him at some points. But it's showing the difference between different radiuses you can measure. And this is for lysozyme, but this is not, you shouldn't take this as read for every protein. The Rg is not always going to be smaller than these other radiuses, depending on what proteins you're looking at. And as Kushal mentioned, actually, the ratio between the radius of hydration or the hydrodynamic radius, say, and the radius of gyration can give you information about the shape of the molecule in solution. He may talk about that in the moles DLS section of the talk. If not, Srinivas and I are happy to chat about that. So there is information contained there, but basically it's telling us something about the size. And it's really the first parameter you get out of SAXS, and almost every SAXS paper you read is going to characterize this RG of their sample. So it's a good way to compare that you're getting results similar to the literature if you know what you're expecting. That's the information the Guinier range analysis can give us. Now the question is, how do you do it? And the problem is it's not quite as simple as just taking a fit, because you have to remember we're fitting an approximation. So you have to carefully pick the endpoints of where you do the Guinier fit so that the approximation still holds. So how do you pick the fit endpoints? Well, the unfortunate and challenging part is that it depends on the particle size and shape. So it's not straightforward. It turns out that the relevant parameter in terms of the scale of where this approximation holds is Q times Rg, which is up in this exponent. So what you really need is for some given size of a molecule, you need Q times Rg to be sufficiently small that this approximation is true. And so what we've plotted up here, this is from a 1987 text that's very comprehensive if you're interested. We plotted the log of I of Q versus QRG squared. And we've done that for 3 different shapes plus the Guinier approximation. And what we're looking for is where these actual scattering profiles for the shapes start to deviate from the approximation. Typically what we say is we fit the Guinier range to a QRG of about 1.3. And that works for globular molecules. If you look at the sphere and the disk, if you go to 1.3 in QRG, they're still pretty much on top of the Guinier approximation. Technically speaking, I think this threshold was chosen to be no more than 10% deviation of the approximation from the actual profile. But it tends to be the field standard. For globular things, QRG of 1.3. But if you look at the scattering profile for the rod, you can see that's deviating a lot early. So for something that's a lot more extended and rod-like in solution, you actually have to do your fit to a much lower QRG. A QRG of 1 should be your maximum for the fit. So you do have to kind of think about the shape a little bit. Yes?
How does this apply to like a multi-domain protein that has maybe like a globular portion and also some kind of like extended portion?
So for the remote viewers, the question is, how does this apply to a multi-domain protein that has a globular portion and maybe an extended portion as well? The answer is usually it's going to look like just one thing, and it'll be mostly dominated by whatever the bigger domain is. If you have domains that are far enough separated in size, you can get 2 distinct Guinier ranges, but that's not a typical experiment for most macromolecules. So typically you'll end up with one thing, and if you know it has some extension, you might start out fitting more conservatively and then see if you can expand it out without affecting
The structure of the target you're looking at is a way to kind of estimate.
So the question is, if you have a structure of the target you're looking at, can you estimate an ideal QRG going in? The answer is probably yes, but nobody bothers. Generally speaking, fit it to 1.3 or 1, see how it looks, and then iterate from there. And indeed, iteration is the way we do this fit, right? Because the RG comes out of the fit, but the endpoint depends on the RG, right? So you pick an initial endpoint, you fit it, you see what the RG is, you calculate QRG for the maximum Q, and then maybe say you got a QRG of 2. Then you adjust it to where 1.3 would be for that RG, you refit it, the RG changes because the fit's changed because you're in the more linear region. You got a new one, different QRG, you iterate that. So generally speaking, this process is iterative. There's software that does a lot of that iteration for you, so you just have to kind of fine tune it. But that's the big idea of how we do this fitting. Is we pick an endpoint, we see what RG we get, we go further in either direction depending on how it looks, and then we go from there. So that's the endpoint. Generally speaking, for a Guinier region, you want to fit to as low Q as your data goes. There are certain cases where you can exclude points at the low Q, but that should be done with caution, and it should not be your usual approach. Don't cut out the low Q data. unless you're really sure you can. And at this stage, I would recommend you consult with an expert before not fitting to the lowest Q, just to make sure something isn't going wrong there. For the minimum Q, to get a good fit, the field generally says that you need maybe the minimum Q times the RG to be less than 1 for globular systems, and we prefer to have the minimum Q times RG less than about 0.65. The minimum Q is limited by the instrument and the setup at the beamline, so this places a limitation on the size of the systems that you can successfully measure at a given beamline. So this, if you have something particularly large, is an important parameter to talk to the scientists about going in and make sure that their beamline can get you a good Guinier range on the sample of interest. I think right now at our beamline, we can get decent Guinier ranges up to globular things of what, almost a megadalton, give or take? So it's sufficient for most systems without any special preparation. But if you need something more than that, we have to change the setup a little bit. So that's how you do a Guinier fit. That's the information you get. The reason we do the Guinier fit first is not because we're particularly interested in the radius of gyration. We're not. I mean, it's useful, but it's not terribly exciting. The reason we do the Guinier fit as the first part of the analysis is because it fits the low Q portion of the data. And as you may remember from a few slides ago, almost every single problem that can show up in your data has some kind of manifestation at low Q. And so when you're doing the Guinier fit, you're extremely sensitive to issues in your data set. Non-linearities in the Guinier analysis are indicative of problems in your sample or problems with your data collection. So if you have aggregation, it causes a characteristic upturn at low Q. This is the question we had before. So I'm showing 3 plots here in the center. There's on the left the one with no aggregate. It has a nice linear Guinier range. It fits very well. The next one, if you try to do a Guinier fit to this range, you can see there isn't a good fit. This is a lot of aggregation. This is like that curve I showed earlier. There's no linear portion of this curve that you can do a Guinier fit to. And if you try to do it, you'll see that immediately. This will tell you there's an issue with your sample. On the right, we have kind of the edge case. There's a little bit of aggregation. There's something really big in solution, maybe some dust or really big aggregate or oligomer affecting just the lowest Q. You can still pick a Guinier range. You can get out an RG, but you should proceed with caution. This will affect the rest of your analysis, this little bit down here. And so you need to figure out if you can still say what you want to about the system, given that you have that influence. You don't necessarily have to throw it out, but you have to be very cautious.
Where should we take a look at it? You're showing QRG, right? What's a Q value?
Sorry, looking for in terms of...
that the aggregation is the characteristic of low Q.
Yeah.
But what's the value of Q you're looking?
Oh, I mean, it's going to depend on the size of the aggregate. But basically, is it showing up in the Guinier fit? You're fitting the Guinier fit to as low a Q value as your beamline measures, right? So if you're going to be able to see it, it's going to show up in the fit. So downturns at low Q. I'm not showing Guinier fits for this, but this is just to remind you that structure factor, usually from concentration, show up as downturns at low Q. Those will also show up in the Guinier fit. Even a little more concretely, you don't just have to look at the fit. You want to look at the fit residuals. So if you have something that's nice and monodisperse, the fit residual should be flat and randomly distributed about 0. If you have something that shows aggregation, you can see even though I've cut off some of the fit here, we're still getting this upturn, characteristic upturn in the residuals. Colloquially in the field, people often refer to this as your residuals smiling at you. If your residuals are smiling at you, it's not good. Likewise, if you have a repulsive structure factor, which I'm showing here, you get a characteristic downturn in the residuals. They're frowning at you. Neither is good. You want these nice, flat, monodispersed, randomly distributed residuals. Both the fit and the residual of the fit give you a lot of information about what's going on at low Q. And these are the things you want to look for. In the software tutorials tomorrow, we'll have examples of both good and bad data, so you can start to get a feel for what this looks like when you're actually doing the analysis. Just to summarize then, the Guinier analysis. It's sensitive to low Q. Most of the problems with your data will show up in the Guinier analysis. You can see aggregation, you can see radiation damage, you can see interparticle interactions, and you can see some types of buffer subtraction issues. The Guinier region, generally, when you fit it, it needs to be linear. It needs to have flat fit residuals. Upturn in the profile or the residuals usually means aggregation. Downturn in the profile or residuals usually means repulsion. Additionally, beyond being a good diagnostic for whether or not your sample's any good, it gives you information on the particle size from the RG, and it gives you information on the particle mass from the I of 0. So it does contain some useful information as well as being a diagnostic. After we've done the Guinier fit, the next thing that we typically do is we do a molecular weight analysis. So as Srinivas mentioned and as Kushal either mentioned or alluded to, molecular weight estimates from SAXS are not that good, actually. They're estimates. Generally speaking, I would say they're about 10% accurate at best, except in exceptional circumstances. So the question then is, why do you do it? And the answer is, you don't do SAXS to determine the molecular mass. Do AUC, do SECMOL, something like that. You determine molecular mass from SAXS to make sure that what's in solution is what you think is in solution. So if you're expecting a monomer, let's say 14.3 lysozyme, and you get a molecular mass of 28, you know you're not looking at a monomer. So this is a very important quality control for your experiments, but I wouldn't do SAXS as a way to find the molecular weight for your system. There are much better ways to do that and much less expensive in terms of sample. That being said, though, there are a lot of ways to try to calculate mass from SAXS, and they all fail under different circumstances, and they all succeed under different circumstances. The first two that I'm showing here, both of these depend on having an accurately measured concentration. So the first one is we can actually calibrate our system, and we do that here at BioCAT, to put the scattering on an absolute scale. If you have the scattering on an absolute scale, if you know the concentration of your system, then if you calculate the scattering contrast, which you can do given a sequence, you can, in theory, calculate out the absolute molecular weight of your system because you know how many electrons it takes to scatter that many photons and things like that. It requires knowing the concentration. So again, if you have a bad concentration measurement, as Kushal said, this method is not going to be very accurate. It also depends on I of 0. It means if you have a bad Guinier fit, this method is not going to be accurate. The next way that we can do this is we can actually do a relative comparison. We can measure a standard protein like lysozyme or glucose isomerase or something like that. And then if you know the I0 for that and the I0 for your own system and you know both concentrations, you take the ratio, you multiply them by the molecular weight of the standard, and in theory, it jumps out with the molecular weight of your protein, right? Because total scattering is just proportional to this molecular weight and the concentration. So we can ratio out the concentration and get just the molecular weight ratio. Now, again, this depends on accurate concentration, but now two measurements of concentration, right? So it's more places to go wrong. I've emphasized that point. So there are two other methods for getting molecular weight from SAXS that I want to talk about. There's actually several others these days, but these are the two other most common ones. So the third, we can essentially calculate the volume of the scatterer in the solution by doing an integral of the scattering profile with a certain weighting. And then, again, we're relying on I0. So all of these rely on I0. All of them need a good Guinier fit. We can calculate this volume. You can multiply by the density of your protein, which you have to either calculate or measure, or you can use a standard, but that's sometimes not right. And from there, you can get out the mass, right? Like a density times the volume is a mass, so this just gives you a mass directly from that. The problem is that this, in theory, requires integrating the intensity out to infinity. Unfortunately, the NIH was not willing to spring for an infinite detector, so we can't actually do that. So there are more advanced techniques that let you account for how much of you're truncating the scattering profile, give you a better estimate of this and a more accurate molecular weight. And we'll actually do all four of these methods in the tutorials tomorrow. The fourth method is called the volume of correlation method. So this is the Porod volume method, I should mention. So the fourth method is the volume of correlation method. So in this case, again, we're calculating essentially a volume. It's a slightly different volume. It's a slightly different integral. And some folks, I guess about 6 years ago now, came up with basically a strictly empirical relationship. They calculated out some coefficients. They found that things basically fell on a line when you plotted this versus the other thing, and using this you can calculate out the molecular weight. So both of these methods do not rely on the concentration of the sample. And that makes them extremely useful as checks for methods 1 and 2. And in the cases where concentration may not be exactly known, like if you've done a SAXS experiment where you're measuring the elution directly from a SEC column, that has some dilution in it. You can measure the UV, but by the time it gets to the SAXS cell, there's a transition time, and that leads to more band broadening. So you don't know exactly the concentration in the SAXS cell. These are usually the methods we use at BioCAT. All 4 methods, though, fail in different ways. They also all fail in the same way. If your Guinier fit is bad, all of them depend on I of 0. One of them depends on RG. None of them are going to work if you have a bad Guinier fit. So if you have aggregates or something else affecting your sample down there, you cannot trust these estimates of the molecular weight. Additionally, so the absolute scale method, it requires accurate concentration of the macromolecule contrast and the partial specific volume. You need to have an accurate concentration measurement, and the absolute scale calibration has to be done right. That's a lot of moving pieces. For the known standard, ideally to get that bang on, the reference standard has to be in the same buffer, or at least a very similar buffer, as the experiment you're doing. It also depends on your concentration measurement for both your sample and the standard. The Porod volume method, first concentration independent method, it works best for compact globular rigid molecules. This is an effect of that integral that you have to do. It also requires accurately knowing the macromolecular density. Kind of most general is this volume of correlation. You don't need a density. In theory, it's relatively good with things that are extended or flexible, but it's very sensitive to noisy high Q data. You need really good measurements far out in Q to really nail this one down. It requires that integral to converge, which again is just measuring far enough out. They have different coefficients for proteins and nucleic acids, which means that it generally fails for protein nucleic acid complexes. In addition, when they did the paper, for reasons I don't really understand, but probably because it stopped working, they didn't fit their coefficients to anything smaller than 20 kilodaltons. It means this approach generally doesn't work for anything smaller than 20 kilodaltons, because they didn't calculate that. So all of these have caveats. So the trick with molecular weight and SAXS is you need to be aware of the different failure modes. It's very tempting to do your experiment to calculate the molecular weight and say, aha, that one is the one that's closest to what I want, that must be the right one. That's not the right way to go about it, of course. What you should do is you should think about the different modes, where they failed, which ones are going to work best for your system, and then when you calculate the molecular weight, look at that one and see how well it compares to what you're expecting. Don't just go with the one that best matches your expectation for the system, because that might lead you astray. The reason we're doing all of this, of course, is verifying that the molecular weight matches the expected oligomeric state in solution. If it doesn't, don't assume you know what's going on. If it's twice, maybe it's a dimer. Maybe you just made a mistake in the calculation. Maybe there's a sample issue. My recommendation in that case, verify with another method. Mols is a great way to do it. AUC is a good way to do it as well. Go back and make sure you really understand what's in that solution that you're scattering. Kushal emphasized this morning, but knowing what's going into the system is what's going to allow you to do the best data analysis once you get the data. So make sure you understand that. Once we've done molecular weight, often the next step, though not always, is to do kind of Kratky analysis. I'm going to talk a little bit about Porod analysis first and then go to Kratky, because Kratky builds on the Porod analysis. Porod analysis, back in, I want to say, the 70s, I could have the timing slightly off there, Porod kind of derived and realized that objects with sharp boundaries, like ideal spheres, have scattering that, in terms of the overall intensity, decays as q to the -4 at wide angles. This is called Porod's law. What I'm showing here is I've taken that plot for two spheres that I had earlier. I plotted it on a log-log scale. And on a log-log scale, the slope of this overall decay is the exponent. So you can see both of these spheres, once you go out to high enough q, have a constant overall kind of envelope for the intensity drop. and it's dropping like q to the minus 4. Now, of course, our systems in solution are generally not hard spheres. Proteins have little bits sticking out. They tend to wiggle. They don't have sharp edges. So the exponent varies depending on what you're looking at. Hard spheres are q to the minus 4. Unfolded random walk polymers are q to the minus 2. Fully extended chains in solution, q to the minus 1. And if you can do this fit and get out this exponent, this is usually done for materials, folks, but you can interpret it in terms of particle shape and porosity. Now, I say this is usually done for materials because for SAXS, generally speaking, we're not getting good enough data out here to really nail the fit down. The data out there is noisy, it's low intensity, and doing the fit can be quite misleading. The other thing I want to mention about this is because we're fitting the high Q, it's really sensitive to the background subtraction. A little bit of offset is going to change that exponent quite significantly. So you really need perfect background subtraction to do this analysis. You need to be really sure of what you've done. Instead of doing fitting the Porod exponent, which can be challenging to do for our data, what we tend to do is we do what's called Kratky analysis. So the basic idea here is we start with what's called a Kratky plot. You plot q squared times I versus q. And so what this is doing is it's weighting that intensity by q squared, which means if you have something that's unfolded, which you expect to decay as q to the minus 2 at high q, on this plot where it's been multiplied by q squared, it instead comes up and it stays constant. So you're seeing here in red on the left what an unfolded system looks like on a Kratky plot. Instead, you have something that's a lot more globular. It's closer to a hard sphere. It has an exponent more like q to the minus 4. It's going to still come up, and then it's going to decay again. Because even after we've multiplied by q squared, it still has a q to the minus 2 decay. So it's slower, but it's going to come up and go back down. Things that have some combination of these types of systems, partially unfolded systems or partially flexible systems, that might come up, come back down a little bit, and then hit a plateau. So instead of trying to do the fit, we can actually just do this transformation and use this plot and be a lot more sure about what we're seeing in the system. The case that isn't shown on this plot, which I stole from a review, is the extended case. In that case, instead of coming up and going flat, this q to the minus 1 fully extended systems just keep on going up. There is, however, a bit of an issue with the Kratky plot as I presented it, which is that when you make a Kratky plot, what the profiles look like on it, the overall scale factor, where they fall in the Q range, depends on the size of the objects you're scattering, on the concentration, and on the overall scaling of the scattering profiles. It's not very good, actually, for comparing two different things. It can tell you what this one thing might be, but it's hard to compare, say, these two curves. Both of these that I'm showing here in blue and in red, lysozyme and glucose isomerase. And on the left, you can see they look very different. They're both actually extremely globular molecules in solution, but they have very different sizes, and they had different concentrations when we measured them, which means they end up looking very different on the Kratky plot. Fortunately, though, there is a way around this, and some very clever folks started using this about 10 years ago now to do kind of extended Kratky analysis. The idea is that we can basically normalize out the effect of the size by normalizing by RG and I0. So anywhere in the Kratky plot there's a Q, multiply by RG. Anywhere there's an I of Q, divide by I of 0. So you end up with a plot that looks like Q RG squared times I of Q over I0 versus Q RG. This takes out all the size, molecular weight, concentration, scaling effects, and puts the profiles, in this case at least, on top of each other, right? This is telling us that these are essentially the same shape once you account for all the overall size factors in solution. So this dimensionless Kratky plot is an extremely powerful way of analyzing your data and looking at differences in shape and conformation. It's often called kind of a semi-quantitative way to look at flexibility. We're not getting a number we can put in the table, but the things on the dimensionless Kratky plot are directly comparable to each other. And so you can make definitive statements about whether things are changing. Again, in this slide, I'm showing a globular system and a completely unfolded system. So completely unfolded systems, these ideal random chains, random walk chains, they're going to come up and they're going to plateau And it turns out the plateau is going to 2 if you can extend it out to far enough QRG. Whereas an extended thing is going to come up and then just keep going upwards. And globular particles, they all, if they're perfect spheres, they're all going to have a maximum at 1.1, maximum of 1.1 at QRG of about √3, which is about 1.73. Any shift in the peak location to the right of 1.3, a shift up, partial plateaus, these are all indicative of kind of a bit more flexibility in your system, depending on what you're seeing. And changes in shape and size are directly comparable because the curves are dimensionless. So this is, as I say, a very powerful kind of semi-quantitative way to get at size and shape changes in your solution, just directly from the profiles. So just to kind of summarize Kratky analysis, the plots inform on flexibility and shape. They're relatively insensitive. Well, let me clarify that. In some ways, so Kratky plots are relatively insensitive to a small amount of aggregates or radiation damage. Because we're multiplying by Q squared, all the stuff at low Q gets kind of squished down and you can't see it. However, dimensionless Kratky plots are extremely sensitive to low Q issues because they rely on knowing RG and I0 accurately. Kratky plots are also extremely sensitive to buffer subtraction issues. So in that way, you can kind of use them to assess buffer subtraction. If you're expecting, say, something very rigid and it doesn't go back down, it can tell you that maybe you have a buffer subtraction problem. But this is a good way to get a feel for what you're looking at in the solution.
Quick question.
Quick question.
By a remote user. Is the dimensionless Kratky being used in most of the software packages these days?
Is the dimensionless Kratky being used in most of the software packages these days? The answer is I don't know. In at least 2 of the 3, let's say, commonly used software packages, dimensionless Kratky is available. It may be available in the 3rd. I haven't used that one in a while. There's also all kinds of homebrew stuff that I have no idea. But in most of the major ones, probably in all of the major ones it is. The final kind of step in basic analysis that you'll typically do is what's called an indirect Fourier transform. If we go back to the very start of the day, which may seem like a while back now, Xiaobing kind of walked you through the math, and essentially the summary was something like the scattering profile is the Fourier transform of the electron. And the question is, of course, can we do a Fourier transform to the scattering profile and get back molecular shape, or at least something that informs on molecular shape? Unfortunately, the answer is mostly no, right? Because the scattering profile is actually a radial average of the intensities of a rotationally averaged molecule. And we've lost all the phases, just like in crystallography. So there's not a particularly good way to directly transform this back to what we're seeing in the system. There is actually, just in the last couple of years, a way to do electron density calculations from scattering profiles, and Kushal is going to talk about that after lunch, or at least briefly mention it. But generally speaking, you can't just take this transform backwards. What we can do, though, if you work out the math, when you do the Fourier transform of the IFQ, what it gives you is it gives you what's called the pair distance distribution function, or the P of R function for short, which is what I'll be calling it. What is the P of R function? Well, the definition of the P of R function is it's the R-square weighted histogram of all possible pairs of electrons, which is, again, this pair distance distribution function. And so the idea is this. Again, I've borrowed this slide from Richard Gilliland's talk. I've got a macromolecule over here on the left, and with these blue bars, I've drawn a bunch of different pairs of electrons in the macromolecule. For the pair distance distribution function, you add up, you draw all these possible bars, every single possible pair of electrons in the macromolecule, and then you create a histogram of how many electron pairs occur at some given distance. And then for reasons related to the transform, you multiply that by R squared. And you end up with this P of R function. It may not look like much, but the P of R function is actually extremely powerful in terms of what it can tell you about your system. Most people tend to just do this, or I don't know about most, many people tend to just make the P of R function on their way to more advanced analysis techniques. Most of the things people tend to be excited about, bead model reconstructions, things like that, require a P of R function as the input. You shouldn't just ignore this, though. There's a lot of really useful information here, and I'm going to go through kind of what that is and how you can get it out. The first is that the overall shape of this depends on the shape of your system. This shoulder here is actually due to the fact that we have these kind of two domains in the system. But even before we get to the shape, the fact is at some point, the number of electron pairs goes to 0. Right? At some point, you reach the total extent of your molecule. So right off the bat, the P of R function is giving you information on the maximum dimension of your macromolecule. So structural parameter as soon as we make it. But beyond that, the shape of the P of R function can tell you a lot about the shape of the particle. This is a set of images borrowed from a really nice 2003 review that's extremely thorough, though a little out of date, doesn't talk about SAXS and things like that. And what we've plotted here is the P of R function for different shapes with the same maximum dimension. We start with a solid sphere in red. That's the center curve here. It looks kind of Gaussian almost. It goes up, it comes back down, it's nice and smooth. Then you look at the rod, which is the green one, and you can see it's extremely different. It comes up very sharply, it has a peak at very low distance, and then it tails off slowly at high distance. So this peak at low distance is coming out of the electron pairs across the short dimension of the rod. And this long tail is coming out of electron pairs along the long distance of the rod. Even just without doing any kind of reconstruction, without doing anything else, if you get something that looks like this, you can say it's mostly spherical. If you get something that looks like that, you could say it's very much like a rod.
Why are these dominated by really low values?
Sorry, what do you mean by dominated by low values?
Why are they peaking at a much lower R?
Yeah, like if it's an interatomic distance, I would assume that the most common interatomic.
Oh, because we're R squared weighted in these.
R squared weighted.
Yeah. Which I think is mostly an artifact of the transform, but has the effect of, yes, suppressing interatomic distances. The other answer is we're not measuring out the high enough Q to get interatomic distances in our data set. So even if it were to show there, we don't have the data to show it. So it's both. So rods have this very sharp peak and tail off. Disks look kind of like a sphere, but a little bit more spread out. Hollow spheres are kind of the opposite of the rod. They have a peak at very large size, which is the distances across the sphere, all the way across the diameters. And they're shorter in the distances just inside the shell of the sphere. Most interestingly, actually, is usually the dumbbell. So here we actually see two peaks in the pink. One of them is coming from all the pairs of electrons inside a single or both of these domains within the domain. And then the second peak comes from the distances between the domains. This is actually very characteristic of what you might see in a multi-domain protein. So this is some real data from proteins. And so just from the shape of the P of R function, you can tell a lot about the shape. So the blue one is a globular system. It looks basically like a sphere. The black one is a multi-domain. You see the domains aren't the same size and necessarily the same separation, but you do have that shoulder on it. This is very indicative of a two-domain system, or more than two-domain, depending on what you have. There's even, you can learn things about flexibility and unfoldedness as well, that I'm not really going to go into. In addition to being the first look at kind of real space shape information for your system, right? This is the first thing we've learned about our system in real space that isn't a size. The P of R function also has other utility. So it can be used to calculate the radius of gyration in I of 0 using the entire scattering profile. In this case, that makes it less sensitive to interparticle interactions. It's less sensitive to aggregates. It's especially useful when you have large particles where you may have a small Guinier range and noisy data. And it's a good check against the Guinier analysis. Ideally, you do both, and they both give you the same answer. If they don't, it's telling you something about your data set, and you ought to be thinking about what that is. There's a lot of information contained in the P of R function, but I haven't yet actually told you how to calculate the P of R function, which might be useful. The first question you might ask is, why can't you just directly do the Fourier transform, right? We have the equation. Why don't we just do the math and get a result? Why do we need the I in the IFT, the indirects? And the answer is this troublesome infinity again. So the Fourier transform requires a transformation of the infinite profile, the finite extent of our measurement, the fact that we have noise in the measurement. Means that if you were to do a direct Fourier transform, it's going to distort the P of R function. You get what are typically called truncation artifacts. Generally speaking, we actually go about this backwards. What we do is we pick a given Dmax, and then we have some set of criteria, and we adjust a P of R function with that Dmax until it fits the data as well as we can. We then adjust this maximum dimension until we get certain criteria I'll show on the next slide. So we're kind of going backwards. So the criteria we use for generating a good P of R function given some maximum dimension. So there is a fitting criteria, right? We say how well does it fit the data set? That's the first step. But we also add in what are called regularization parameters. So we've lost information when we do this experiment, right? We have all these, the phases go away, there's a bunch of averaging. So we have to add information back in somehow. And so we say things like, oh, the P of R is probably relatively smooth, right? We don't expect really rapid variations in the number of electron pair distance. We say things like, oh, well, we shouldn't get big systematic deviations from the data set, even if the chi-squared is looking okay. The solution generally should be positive, because negative electron pairs don't make sense, except in certain situations where you have lipids and they end up below the contrast of the liquid. We also make conditions on the stability of the solution. If you change the parameters you're using to generate the solution a little bit, the solution shouldn't change a lot. So these are the kinds of extra bits of information we can apply to get better results than just doing a direct transform backwards. Most commonly, to do this, you'll use a program called Genome, which is in the ATSAS package. Other programs do exist, but I'm going to focus on that just because it's the most common one. And so this program, like many of them, requires an initial estimate for the Dmax of your inverse Fourier transform, of the P of R function. And so a lot of the art of getting a correct P of R function comes down to picking a good Dmax. So the criteria that we use for Dmax is basically looking at the P of R function and saying, does it look right? And that's a little bit of an odd thing to say, but I'll talk about what that means. What I've plotted here are three different P of R functions. There's one in red, which is kind of hidden under the other ones, but you can kind of barely see, which has a Dmax in the middle. There's one in black, which has a shorter Dmax, and one in blue, which has a larger Dmax. The statement, kind of the general guiding principle behind all of this, the statement that we make is that your P of R function should fall gradually to zero at Dmax. And this has a fundamental physical interpretation. The idea is that given some maximum dimension, given some macromolecule, right, it doesn't have a hard cutoff. It's not a hard sphere. So you have, maybe little wiggly side chains, you have maybe a little wiggly N or C terminus, something like that. Whatever it is, there's even just a little flexibility in the system. You're never going to have this really sharp cutoff in your electron pair density. So you always expect it to kind of gradually decrease at the very end and tail out. If you pick a Dmax that's too short, when you're guessing what the Dmax should be, it's going to artificially force the P of R function to zero. It's going to come down very sharply. If you pick a Dmax that's longer, it's going to wiggle about the origin and not really give you any more information. We can tell if we've under or overestimated the Dmax just by looking at these criteria. Now, the way people generally describe it is you want your P of R function to end like you want your plane to land. You want your plane to come down like this and kind of gently touch down. You don't want your plane to do that. You don't want your plane to do that, right? So nice, smooth plane landing for the end of your P of R function. There are some additional criteria we can use for generating the P of R. We can compare the RG and the I0 to the Guinier fit. Those should fit well. Generally speaking, we force the R to zero at R0, force P of R to zero at R of 0 and R of Dmax. You can turn off the forcing at Dmax and see if it stays at 0, or if you've artificially forced it down. And then finally, of course, you should check that the transform actually fits your data. So all these other criteria can be right, but you can have a bad fit against your data set. And this is very much a heuristic approach, right? There's no necessarily right answer. And my rule of thumb is that, generally speaking, even for good data, uncertainty in determining Dmax can be as much as 10%. There's going to be a range in which it'll look pretty okay. So if you have a Dmax change from like 40 to 41 between two different samples, that's probably not significant unless you can back it up with some other evidence that something has changed. Most likely that's just a result of your estimation. So this is what a good P of R function should look like. This is what I was showing on the previous slide, but it was kind of hidden. You have the system, you have a nice smooth approach to the maximum dimension, you have a good fit to your data set. Ideally, you'd check the residuals on this as well. I haven't plotted that here. In addition to the Guinier fit, the P of R function is where you can catch a lot of the problems with your data set. So aggregation in particular shows up here very strongly. Typically what happens if you're doing an IFT and you have aggregation in your system, question, yes? Yes. Yeah, so for the remote users, the question is, what are the two bumps on the P of R plot telling us? In this case, this is actually a little bit odd. This is a ring. So this one is corresponding to the cross ring distances, this bigger peak, and the smaller one is corresponding to the distances within the ring itself. So it's similar to a two-domain system, but it's a little bit reversed. This is much more like the hollow sphere, where we had the largest peak at the highest size. So the question is, if you have a multi-domain protein, do you always get distinct peaks, or can you get a shoulder? The answer is usually you just get a shoulder. It's usually not separated enough to give you distinct peaks in the P of R. You'll get something, I think I can go back a few slides, you'll get something like this black curve, where you have a shoulder on the main peak. So aggregation and IFTs. So this is very characteristic. If you have a system with aggregation, so here's the same protein with and without aggregation. When you have aggregation and do an IFT, you'll see that you get this long tail that just kind of extends out and out and out. I've actually run this out to about 4 times the maximum dimension. Even at that point, you can see I'm still forcing it to 0. So there's a lot of kind of variable size aggregates in this system, and it's not coming to any kind of conclusive maximum dimension. You could probably keep extending this out essentially to infinity, as good as our data is, and not ever see something that's going naturally to 0. So it's very sensitive to these kind of aggregates in solution. You can see kind of a similar effect, but less dramatic with flexibility. You'll get something where there's a lot of stuff really close to 0, and then eventually it goes to 0, because there's a wide range out there where it's kind of flopping around, and there's a few things in your ensemble that have really extended conformations that you're sampling. So this is a very telling sign of aggregation. Usually it ends up meaning there's no good way to pick a Dmax. So you have to be careful with that. And it's a good analysis technique. If you have interparticle interference in your P of R, what it looks like, as Kushal briefly mentioned, is that you get a truncated Dmax and the overall size of the thing is going to go down. This is a lot harder to tell, because without knowing what the Dmax actually should be, it's hard to know if you've truncated it or not. In a couple slides, I'll show you another way to look at this that's a little more informative, but this is what the effect will look like. So it is also sensitive to interparticle interference. A few more slides in summary. The P of R function provides real space structural information about the shape of the macromolecule. It provides an estimate of the maximum dimension and more accurate determinations of RG and I0. It's sensitive to aggregation and interparticle interference, and it's generally required before moving on to more advanced analysis. So I know this is a lot of information, so I'm going to give you a couple summary slides that are hopefully useful to refer to. So this is the same plot that Kushal showed from that Jacques and Schruella 2010 paper. This is a very good resource for seeing a lot of the effects that we just talked about, what effects they have on different portions of your profile. So they have good data on the left-hand column with a Guinier, a P of R, and then a P of R where they've extended the Dmax. They have interparticle interference in the center column, aggregation in the right column. So you can see the effects on the Guinier, you see the downturn, you see the RG goes down, or the upturn and the RG goes up for interparticle and aggregation. P of R, you can see we truncate the P of R, or we have to artificially force it, depending on which one we're looking at. And then this is kind of the interesting point that I wanted to mention, is that if you do have interparticle interference and you extend out this Dmax, often you'll see a negative dip. It'll go down, instead of oscillating right near 0, it'll stay negative. question. Yeah.
How can you call
This is the radius of gyration. So the radius of gyration is actually much more accurate than that, assuming you have a good Guinier range. But good question. The question was, how can you tell if these are different? And the answer is it wasn't Dmax. But lots of information, so I appreciate the clarification. So for interparticle interference, if you extend out Dmax beyond where you think it should be, you often see it dip below 0 instead of just oscillating about 0. Whereas for aggregation, if you extend it out past where you think it should be, you'll see it never really goes to 0 very well.
That negative dip, is that real? Is that because you actually don't have any particles that are that far away?
So the question for the remote users is this negative dip in plot K real? I'd have to think about it a little bit. My instinctual answer is no. It's an artifact of how the fact that we're trying to fit a structure factor as well as a form factor with something that's just trying to fit a form factor. So it has to add in some negative density to do that. You can get real negative dips if you have lipids in your system. Lipids actually scatter less than buffer, so they end up looking like negative electrons. So if you have, say, a protein embedded in a lipid nanodisk, it's very characteristic. It'll go up initially, come back down at the nanodisk point, often dip below 0, and come back up. So in that case, it is a real. But for the interparticle interference, I don't think it is. Couple of questions.
Remote. So one is, would you recommend that one always extend out the Dmax range to verify?
So yes, I would. Actually, the way I tend to pick Dmax, I'll let it. The program will automatically tell you generally what it thinks the Dmax is. I then tend to double or triple that, see what the profile looks like, see what the P of R looks like, see if it's naturally dropping to 0 where it picked the Dmax, and then come back and iterate around the range where it naturally drops to 0. And we'll go through this in the software tutorials tomorrow. I know the remote users don't get those, but they're self-guided. You have the PDFs, you have the example data, you can work through them as well.
Second question is, it's a callback. How do I know the Guinier range for my molecule, especially if it is not spherical?
So how do you know the Guinier range for your molecule, especially if it's not spherical? The answer, well, there's two answers. So if you know it's not spherical, start with a Q max times RG of 1, because that's kind of the strictest you need to go, and just fit that limited range. Once you get a good fit in the limited range, then extend it out further and see if the RG changes and if the residuals go nonlinear or non-flat. Kind of more concretely, you have to do it, to get a Guinier fit, you have to do it iteratively. You pick a point, you get the RG, you calculate the Q max times RG of that point, you see if you need to pick a point that's further in or further out, and you iterate on that until you come to a solution. And the software does a lot of that iteration for you, but you usually have to fine-tune the endpoints a little bit. More questions? Or all right. So I have another question. The third row and the fourth row, yes. So the difference between the third row and the fourth row is that what they've done in this fourth row is they've extended the Dmax out to something much larger than what they were seeing here. So you can see in this case the Dmax is about 45, in this case it's 100. And so for something that's well behaved, you shouldn't really get any additional information in the P of R function. It should be flat and it's probably just going to oscillate about 0 a little bit. Whereas for something that isn't well behaved, it's going to show you a pathology like we're seeing in the bottom two plots. Okay, so just to give you some summary bullet points you can refer back to if you're in a hurry. So summary for data validation. Guinier fit shows most of the issues. So always do your Guinier fit first. P of R function is good for catching aggregation and interparticle interference. The molecular weight is necessary to validate what you have in solution. Make sure you pick a method that is appropriate for your system, not the method that gives you the answer closest to what you want it to be. The Kratky plot is particularly sensitive to background subtraction. So in terms of the data analysis, then, what these give you, the Guinier plot gives you the radius of gyration in I of 0. It is sensitive to data quality issues, so you have to be careful with the Guinier fit. The molecular weight is relatively unreliable, 10%-ish maybe, but it is required to validate what state or sample you have in the solution. These days, I don't think you're going to publish a SAXS paper without an estimate of the molecular weight that you had in the solution. And pick the right calculation method. The Kratky and dimensionless Kratky plots provide extremely powerful analysis for flexibility and shape, especially comparative analysis. The P of R function provides real space shape information, an estimate of the maximum dimension of the particle, and a potentially more accurate determination of the radius of gyration in I of 0, also sensitive to data quality issues. And finally, the P of R is generally required before moving on to advanced analysis techniques. So that's the brief summary. I'll take any more questions, and then we'll break for lunch.
How to do buffer subtraction correctly?
How to do buffer subtraction correctly? Match your buffer correctly. Really, that's the only thing you can do. Use a dialysis buffer. Make sure your instrument's stable, which is not really your responsibility, but our responsibility. And then your buffer subtraction ought to work out. So we harp on it a lot, but once you get to the point of making the measurement, there's not really anything you can do. So you have to do it in your lab, you have to do the dialysis, and that'll get you there.